Okay, so you should be now able to hear me. Um, yeah, you should be able to hear me now. Yeah, perfect. So we are live on Twitch. Let me just mute myself over there and there. So I'm live on Twitch and also um, on YouTube, but I think the screen is too big. So let me adjust this a little bit. Still not the best. Okay. Then in that case, let me switch over. Let me just close this for a second. This one. Okay. Just turn that on. Okay, that should be much, 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 much better now. And it should be also visible. Okay, let me change the name very quickly. So this is learning AI and software engineering, I would say. Similarly, I would do the same for YouTube as well. So I'm going to rename this to learning AI and software engineering. Let me save that. Okay, so that's that. Now let me see if I can. What happened to my? Multi-chat is not working. That's working. Let me just do it like that. Okay, so the first thing, um, yeah, so there were two things that I wanted to do. The first thing was I wanted to implement ImageNet. So let me just quickly download this. Okay, so ImageNet. Let's take a look. ImageNet classification with deep convolution neural networks. Okay. We trained a large deep neural CNN network to classify. So they're training a CNN model, and it's classifying 1.2 million high resolution images of the ImageNet. Okay. So let me create a new notebook over here for our notes, right? So on the test data set, we achieved top 1 and top 5 error rates of 3.7. Okay, so these were the results. Let me do this with a different color. So these were the results, which is considerably better than the previous state of art. The neural network, which has 16 million parameters and 650,000 neurons, consists of 5 deconvolutional neural networks, some of which are max pooling layers and 3 fully connected layers with final 1000 softmax. So this basically is the architecture, and usually I'm keeping my architectures with a red color, no, with a green color, and I'm assigning my data sets with an orange color or maybe like a red color. So to make the training faster, we started with non-saturating neurons and a very efficient GPU implementation of the convolution operation. Okay, so this is more into experimental stuff. So experimental, let me put that as blue. To reduce overfitting in the fully convolutional neural network, we employed a recently developed regularization called dropout. So this is where they invented dropout. This paper, I don't know when it came out, um, but yeah. So they're implementing dropout over here. Okay, so dropout. This also comes in the regular implemented dropout. Okay, let's change the color back to something like red again, or no, not red, green. Okay, all right. Um, hmm. Okay. Um, to reduce overfitting in the fully connected layer, uh, can I edit this into? Okay, that proved to be very effective. We also entered a variant of this model in the okay, so this was the competition where it achieved this results. So this comes again in the results part. So these are the results again, and this will go back to purple. Okay, current. So we have introduction, we have the dataset, and we have the architecture. Local response normalization, overlapping pooling, overall architecture, reduce overfitting, augmentation, dropout, details of learning, and the results. Qualitative evaluations. Okay, let's start with the introduction, I would say. Okay. Current approaches to object detection make essential use of machine learning methods to improve their performance. We can collect larger datasets, learn more powerful models, and use better techniques for preventing overfitting. Okay, until recently, datasets for labeled images were relatively small, on the order of tens of thousands of images, which is these are the images. So these were like some of the other previously other data sets which were used for convolutional neural network stuff. Simple recognition tasks can be solved quite well with data sets of this size, especially if they are augmented with label preserving transformations. Okay, for example, the current best error rate on the MNIST data digit recognition task is less than 0.3%, approaches human performance, but objects in realistic settings exhibit considerable variability, so to learn to recognize them is it is necessary to use much larger training sets, and indeed the shortcomings of small image datasets have been widely recognized, but it has only recently become possible to collect labeled datasets with millions of images. The new larger datasets include LabelMe, which consists of hundreds of thousands of fully segmented images, and ImageNet, which consists of over 15 million labeled. So they're talking about different datasets. LabelMe, this is also a famous dataset, but I think the more widely uh, known dataset is the ImageNet dataset, which we will be working with, I think, in this paper. To learn about thousands of objects from millions of images, we need a model with a large learning capacity. However, the immense complexity of object recognition tasks means that this problem cannot be specified even by the datasets, as large as ImageNet. So they're trying to say that previously how people were getting away with deep learning was that they were training the models on very big data sets. And now that you can't do that, um, even if you have like ImageNet, which has like 15 million labeled high resolution images and over 22,000 categories, you need your model to be more complex. So our model should also have lots of prior knowledge to compensate all of the data we don't have. Uh, okay, so sorry. What it means is that there's a rich amount of knowledge or complexity of or some sort of like complexity involved in object recognition task, which cannot be specified even with 15 million images, and it has to be um, somehow extracted by our model. Anyways, CNN constitute one such class of models: 16, 11, 13, 8. Okay, these are the references. Their capacity can be controlled by varying their depth and breadth, and they also make strong and mostly correct assumptions about the nature of things, namely stationary of statistics and locality of pixel dependencies. This is pretty interesting. So let me put this into something other. Look into this in detail. Okay, so these are some of the qualities I think for CNN models. Moving forward, thus compared to standard feed-forward neural networks with similarly sized layers, CNNs have much fewer connections and parameters, and so they are easier to train, while their theoretically best performance is likely to be only slightly worse. Okay, so CNNs are pretty good. Despite their attractive qualities of CNNs and despite the relative efficiency of their local architecture, they have still been prohibitively expensive to apply on large scale to high resolution images. Luckily, current GPUs paired with highly optimized implementation of 2D convolution are powerful enough to facilitate. Yeah. Okay, so they're saying that you can train the ImageNet on CNNs now without severe overfitting. The specific contribution of this paper are follows. We trained one of the largest convolution neural networks to date on the subsets of ImageNet used in this particular. I think this was the competition. Yeah, this is the competition. Uh, yeah. Okay. Mm-hmm. All right. Okay, where were we? Yeah. And achieved by far the best results ever reported on these data sets. We wrote a highly optimized GPU implementation of 2D convolution and all other um and where was I? Of the convolution neural network and all other operations inherent in training of convolution neural networks which made available publicly. What does it mean publicly? Our network contains a number of new and unusual features which improve its performance and reduce its training time, which are detailed in section 3. Okay, so let's highlight this part. The size of our network made overfitting a significant problem, even with 1.2 million labeled training examples, so we use several effective techniques for preventing overfitting, which are described in section 4. So this is the section where they're explaining how they mitigated the overfitting part of the model. Our final network contains 5 convolution, 3 so there are 5 CNNs, 5 convolution, and 3 fully connected layers. And there's this depth seems to be important. We found that removing any convolution layer, each of which contains no more than 1% of the model parameters, resulted in inferior performance. Okay, in the end, the network size is limited mainly by the amount of memory available on current GPUs and by the amount of training times that are willing to tolerate. Our networks takes between 5 and 6 days to train on two GTX 5083 GPUs. All of our experiments suggest that our results can be improved simply by waiting for faster GPUs and bigger datasets to become available. So luckily, since we're doing this in 2026, we have available of better GPUs on on Google Colab, so this won't be that difficult to train. ImageNet is a dataset of over 15 million labeled high-resolution images belonging to roughly 22,000 categories. The images were collected from the web and labeled human labelers using Amazon's Mechanical Turk crowdsourcing tool. Okay, what's this? What's this? Amazon Mechanical Turk crowdsourcing tool. Whoops. Amazon SageGround Truth allows you to easily build and manage your own data labeling workflows and workforce. Okay, so they use some sort of this labeling tool. Interesting. Starting in 2010, as part of the Pascal Visual Object Challenge, an annual competition called the ImageNet Large Scale Visual Language Challenge, which they have now mentioned, this has been held. This uses a subset of ImageNet with roughly 1,000 images in each of the 1,000 categories. In all, there are 1.2. So this is where they're explaining the data set. So this is important for us. Dataset information regarding so you have 1,000 images with in each 1,000 categories, so that's 1,000 by 1,000, 1,000 by 1,000, and then you have that they're saying that you have 1.2 million training images and you have 50,000 validation images, and that you have about 150k, let's just do Ks because that's more easier to write, testing images. Okay, is the only version of for which the test labels are available. So this is the version on which this competition in section 6 we report our results on this version of the dataset as well, for which test sets label are unavailable. On ImageNet, it is customary to report two error rates, top 1 and top 5. So top 1 and top 5 is basically their evaluation metrics, which they are repeating over and over again. So let's do this. And let's do this as a comment. This is the evaluation metrics. Change that to, I think I'll put that as blue. Okay. All right. Moving on. ImageNet consists of variable resolution images, while our system requires a constant input dimensionality. Therefore, we downsample the images to a fixed resolution of 256 by 256. This is very important. Given a rectangular image, we first rescale the image such that the shorter side was outlined 256, and then cropped out the central 256 by 256 patch from the resulting image. We did not pre-process the images in any other way except for subtracting the mean activity over the training set from each pixel. So we train our network on the center draw images. So this is where they're explaining the pre-processing part. Pre-processing of the data set. Architecture. All right. The architecture of our network is summarized in figure 2. It contains 8 layers, 8 learned layers. So let's take a look at the architecture. So this is what they're explaining. An illustration of the architecture of RCNN explicitly showing the delineation of responsibilities between the two GPUs. One GPU runs the layer parts at the top of the figure, while the other runs the layer parts at the bottom. So I'm assuming that one is running this particular part and the other one is running this smaller part. The GPUs communicate only at certain layers, so maybe over here. The network's input is 150 this much dimension, and the number of neurons in the network's remaining layers is 253,440,18 something something to 1000. So I'm assuming that this number over here, this is basically 2048 times 2048, which basically equals to 253,440. Let me confirm that. So we will take our calculator, 2048 times 2048, and that is not this number. Okay, maybe it's 128 by 128. No. Uh, so the input is 150 by 528. So 256 by 256. No, it's not it. Okay, that is a problem. So I mean, what is 248 by 248 again? Should be this, but they're saying it's 490,409, so they're adding it. So that's like 2048 plus 2048. But why are they adding? It's telling about the number of neurons. Oh, I thought it was the number of parameters. So this basically they're saying this is 1000 and then you're adding these two up. That's the total amount of neurons over here. Same over here. And then this will be 128 times 13 times 13 times 2. So that's this one over here. Let me just write this down. So this is the last layer where you're applying the softmax, I think. This is going to be 2048 plus 2048, so that's 4096 total neurons. Similarly over here, then this one is, sorry, this one is basically 128 by 13 times 13 times 2. So that is 21632 times 2. That makes it 43264. Bottom layer plus the top layer, and then so on and so forth. I think then it's the same over here, it's the same over here, and then that's this one, and then you have this much over here. Okay, let's get back and let's start reading a little bit on the architecture. So they mention that they have 8 learn layers, they have 5 convolution and 3 fully connected layers, right? And I'm going to jump back and forth a lot. I wish there was a way how I could just split this so that I don't have to do this. Wait, let me see. How to split window in Adobe Reader. Split view, sorry. Ah, it's in the Pro version. I don't think I have the Pro version. Damn it. Wait, let me check. Uh, so there's window.
Today I'll be using Adobe Acrobat D a PDF into multiple. PDF.
I do not have the option to split up. Why do not I have the option to do? What did that do? Do I have the option of splitting my window? Do I have the. I don't think so. No. No. Damn it. Okay, so back to the. I mean, I can do it like this. Not the most practical way of doing it. But it is what it is, so there we go. Okay, let me see. Okay. So let's put the architecture somewhere here. Let me zoom in that so that we don't have to look over it over again. And then we can continue over here. And let's zoom out a little bit out. Okay. So, ReLU non-linearity. So this is the activation function that they're using. The standard way of using a neuron's output f as the function of its input x is the tan h x, or the 1 plus e minus x minus 1. So let me bring out the activation functions. Activation functions. So you have a lot of activation functions. You have the sigmoid, which is 1 over 1 plus e minus x. You have the tanh one, you have the ReLU, and then you have the leaky ReLU. So they're basically saying in terms of like training time with gradient descent, these saturating non-linearities are much slower than the non-saturating non-linearity of this. So they're saying that the tanh one, or the most famous sigmoid function, um, they're really slow. So let me just add that point. Sigmoid activation function plus the tanh um, activation function, which they're calling these as them both. Both of them are saturating non-linearities. Why are they called saturating? Question mark, question mark. That's something that I will read on, or I can just search that. Why is sigmoid and tanh called saturating nonlinear functions? Sigmoid and tanh, I'm using right now AI, Google Gemini's AI. Sigma and tanh are called saturating because of their outputs are flattened out. Yeah, I thought so too. I thought so. That was like a random guess in my head, which is that if you see the activation function, so let me show it where. For the sigmoid, see if I can. For the sigmoid, it's tapering off at its end. Similarly for tanh, but for ReLU and for leaky ReLU and for ELU, which I've never heard before, you can see that it's not saturating that much. That's pretty good. Okay, coming back. Okay. So you're using this because this is really fast, I think. Following the Nair and Hinton, we refer to neurons with this nonlinearity as rectified ReLUs. Deep CNNs work with ReLU strains several times faster than their equivalent tanh. So they're basically saying that ReLU trains faster. This is not the data set. This is more about the implementation. So let me do this. Oh, it is green. Yeah, green, green, red. Okay, this is demonstrated in figure 1, which shows the number of iterations required to reach 25% the training rate on CIFAR 10 dataset for the particular four-layer convolution network. This plot shows that we have not been able to experiment with such large neural networks for this work if we had to use traditional saturating neural models. Okay. So this is basically saying a four-layer CNN with ReLU is the solid line, which is 25% faster, the lesser training error rate, than the dashes one, which basically used the tanh one. The learning rates for each network were chosen independently to make training as fast as possible, no regularization or any kind of employ the magnitude. Okay, moving on. This plot shows this. We are not the first to consider the alternatives to traditional neural network, the neural models and CNNs, for example. claim that nonlinearity of the mod of tanh works particularly well with their type of contrast normalization followed by the local average pooling on the Caltech 101 dataset. However, on this dataset, the primary concern is preventing overfitting, so the effect they are observing is different from the accelerated ability to fit the training set which we report when using ReLUs. Faster learning has great influence on the performance of large models trained on large datasets. Okay, this is I will ask about this because I'm a little bit unsure what they're trying to say over here. But I think what they mean is that there was another research group which used the modulus of tanh and they used local average pooling, which made their training faster. Or not faster, but it prevented overfitting. Yeah. So this was done um with keeping of mind that they wanted to avoid overfitting, whereas over here they're trying, or the author of AlexNet, they're trying to see how fast they can train on large data sets. Okay, so moving on. um uh with training on multiple GPUs. Okay. Hmm. So we're on 3 out of 9, I think. That's 6 pages more. I mean, 3 is about to be finished. A single GTX 5080 has only 3 GB memory, which limits the maximum size of the networks that can be trained on. It turns out that 1.2 million training examples are enough to train networks which are too big to fit on one GPU. Therefore, we spread the net across 2 GPUs. Current GPUs are particularly well suited to cross GPU parallelization, as they are able to read from the write to one another's memory directly without going through the host machine memory. The parallelization scheme that we employ essentially puts half of the kernels or the neurons on each GPU, with the additional trick, the GPUs communicate only in certain layers. This means that, for example, the kernels of layer 3 take inputs from all of the kernel maps in layer 2. However, the kernels in layer 4 take input only from those kernel maps in layer 3, which reside on the same GPU. Choosing the pattern of connectivity is a problem for cross validation, but this allows us to precisely tune the amount of communication until it is a acceptable fraction of the amount of computation. Okay, this is where they're explaining how they're basically using or utilizing 2 GPUs for this task. Um, for replicating this, I mean, I can do it in one GPU. I do not require 2 GPUs. But for the sake of replicating it one to one, maybe I will also look into this. So GPU parallelization, parallelization. I think there's one R, parallelization trick. Okay, the resultant architecture is somewhat similar to that of the columnar CNN employed by this series, except that our columns are not independent. This scheme reduces our top 1 and top 5 by 1.7 and 1.2% respectively, as compared with a net with half as many kernels in each convolution layer trained on one GPU. The 2 GPU net takes slightly less time to train than on the 1 GPU net. The 1 GPU net actually has the same number of kernels as the 2 GPU net in the final convolution layer. This is because most of the net's parameters are in the first connected layer, which takes the last convolution layer as the input. So to make the two nets have approximately the same number of parameters, we did not have the size of. Therefore, okay. I'll put this into something which I did not understand in the first read. Okay, local response normalization. Oh. ReLUs have desirable property that they do not require input normalization to prevent them from saturating. If at least some training examples produce a positive input to a ReLU, learning will happen in that neuron. Okay. Yeah, I think I'm going to pause over here for now. Um, I might return back to this paper afterwards. But I'll switch to something else now. Also feeling a little bit sleepy. But yeah. Or do I complete the methodology part, which is still here? I think I'll complete it. Okay. ReLUs have desirable property that they do not require input normalization to prevent them from saturating. If at least some training examples produce a positive input to ReLU, learning will happen in that neuron. However, we still find that following the local normalization scheme aids generalization, denoting by AIXY the activity of a neuron computed by applying kernel I at position XY and then applying the ReLU nonlinearity. The response normalized activity BIXY is given by the expression this, where the sum runs over the n adjacent kernel maps as the same position, same spatial position. Oh gosh, I'm yawning too much. I will definitely do this afterwards. Okay, good. Good. I did wanted to learn a little bit about Kafka, so I'll start with that. So let me close that. Let me save this to wherever this was saved previously. And let me just cut this to here. Okay, moving on to I have to select the path. I don't like selecting paths. Okay. Mount D to projects and then learn Kafka. Okay, so basically, the right now I'm trying to learn how to use Kafka. So I'll be replicating a video by Tech World with Nana related to Kafka. That's basically my plan. So you will probably not hear any audio because I haven't turned on the desktop audio, but I think you can still hear the audio through the microphone. But yeah, basically my goal is to replicate this one, which is Kafka Crash Course Hands-on Project by Tech World with Nana. So I'll do that
we are diving into Kafka. First, by understanding conceptually what Kafka is and why it was developed,
So,
or I'll start.
do I have my Notion notes? Do I have my Notion notes? Do I? Do I? Do I? Do I? Do I? Do I? Mm, did I not make them over there? There we go. Um, okay, so let me just show this. Yeah. So basically, you have Apache Kafka, which is, from what I understand, it's a publisher subscriber model where you have your producers and you have your consumers, and if you get any one event which is caused by the producer and you want to then execute like a chain of commands without the system failing, you're basically using Kafka. So the way how this works is you have your events which are saved as topics. So your topics would be like payments, inventory, invoice, which is organized as a group. So orders, inventory, and yeah, let me just
Startup. So we
watch the
begin
video again.
with a simple architecture where microservices for orders, payment, invoice, and so on just directly call each other. And this works fine until our online store becomes really popular. Plus, we announce Black Friday sales, and suddenly, with thousands of users placing orders and checking out all at the same time, our application crashes under load like items on a conveyor belt. And this is where Kafka comes in. Think of Kafka as a middleman between these microservices. So instead of services talking to each other directly, they use Kafka as a middleman to communicate. The order service hands an event to Kafka saying, hey, an order was just made with these details. Can you just let all the other services know and just continues its work without waiting for a reply? So it doesn't wait there to make sure the payment and other services receive that information. It
All right, so I'm gonna end the stream now. I'm probably gonna start with Kafka and continue with the research paper tomorrow. I think it's almost like an hour mark. I think just 2 minutes are remaining, and then it will be a total 1 hour stream. Probably I'll do a much longer one tomorrow. Um, but yeah, I'll see what I can do tomorrow then. All right, then have a nice day or night, and see you guys tomorrow. Bye bye.